Hey everyone, welcome. Today we're going to talk about stream gatherers. So, I'm Viktor Klang and I work at the Java Platform Group at Oracle as a software architect. And I've been working on stream gatherers for a while, so I thought it would be a good opportunity to share some of the recent work there. So, before we start, so how many of you are familiar with the java.util.stream.Streams? Most. Right? It's a super popular part of the java.util collection library. And just before we start, I like to explain some of the anatomy parts so we know that we're talking about the exact same things. So this, for all intents and purposes, this part is a source of information or elements. And there are many different ways to obtain sources of elements, right? You could have an array list that you have elements from, or you could have a generator, right, if you so will. And then these parts are intermediate operations. So they're almost guaranteed to be followed by a terminal operation that does something with the stream. So it's sort of a builder pattern where you have a source, you potentially add some intermediate operations, and then you add a terminal operation, and then something gets done. Now, how is that done? Well, you could do it sequentially, or you could do it in parallel. So that's going to be one of the topics that we're going to touch upon during this presentation as well. So for all intents and purposes, the entire thing, which is not a real thing because you cannot have a reference to it, but let's call that a pipeline. So when you've bunched everything together, that's your stream pipeline. All right, so during this presentation, my goal here is for you to think about this. What if you could have any intermediate stream operation? Not only the built-in, like filter or map or flat map, but if you could have any intermediate operation, what would that enable for you? So, Stream has a few intermediate operations already, but how do you decide which intermediate operations? Because there are an infinite amount of potential intermediate operations for different domains, for different use cases. But how do you decide which things go in to be callable on the stream interface? How do you decide what is important enough to go in? So we were thinking about this because there has been a few new operations being added, like take while, etc. But if they aren't in place and you need them, and there's no way for you to build your own, then what do you do? So as an example, look at this. We have some source of information, and we want to have an intermediate operation that does the equivalent of if there are consecutive duplicates in this stream, drop them. How would we implement this on stream? Like, we can't use filter because we can't remember the previous element, right? So we might be able to implement this as a collector. But that means that we now are outside of the stream because collect is a terminal operation. So we're sort of left with, what do we do? Or you need to do any sort of windowing on a stream. You need to group individual elements into other, like a list or something, depending on some condition. How would you do that? So in this case, for instance, this is a window fixed operation or a fixed window operation of 2. What if we want to do something more sophisticated, like having an incremental roll-up of an aggregation? This is called a scan operation. So how do we do that? Because we still need to remember something. We need to have a stateful intermediate operation that is able to emit things, but also remember things. How do we do that? So I'm going to try to answer this question first. So how many of you have used collector or even defined your own collectors? So most of you? So your first question might be, why is not collector enough? To answer that question, we need to first decide which features do we need. So an intermediate operation could have any-to-any input to output. So we consume one element and produce none, or 5, or an infinite amount of elements, or it changes between every single element that it encounters. So there's lots of different types of combinations that we're going to need to support. Also, if we need to support infinite streams, can we use collector? Because collector cannot tell us when to stop. So we would have to collect everything. And depth first means that if you have multiple intermediate operations, if you need to consume all upstream elements before you can start to emit them downstream, you clearly couldn't do that for an infinite stream, because you wouldn't have infinite storage. So depth first means pushing through the results of each application of each intermediate operation to the next, and so forth. Stateful or stateless operations. Sometimes we need to remember things between each element, and sometimes we do not. Perhaps poor terminology, but some operations do not want to consume the entire stream. Take limit as an example. You want to limit the stream according to some number of elements, or perhaps according to some predicate or something else. You want to be able to exit early. Sequential or parallelizable. So some operations are inherently sequential. So if you're doing windowing, for instance, you're going to have to bunch things together according to their encounter order, and as such, that becomes an inherently sequential operation. How do you do that with a collector if you cannot do anything but supply a combiner? So if you have to supply a combiner, that means it needs to do the correct thing under parallel evaluation. And how do you do that for something which is inherently encounter ordered? It's just not possible. Also, an important part is sometimes you do not know what the end result is unless you know that there are going to be no more elements being passed down. So if you're doing a sum, for instance, you wouldn't know to emit the end result if you didn't know there was no more elements coming downstream. So having some form of callback for this would be important. All right, so let's say that these are our requirements. Well, looking at collector is an interface. T is the type of input elements to the collector. A is the type of the accumulator or the state, and R is the result value or type. So we have sort of a bag of functional interfaces that are exposed by collector. So the first one is a supplier of the state. So we know how to construct a part of the state that we're going to need for this collection operation. We have an accumulator, which is a by consumer that gets the current state and the next element, and you can decide to do whatever you want to do at that point. And then in order to combine the results, so if you do a forking of the source elements, and you split that into a tree, and you do the work in parallel, and now you need to join. You've forked, you've done the operation, and now you need to join. So you need a combiner operation in order to decide how do I join this correctly so that we can yield the result at the end. And then, of course, we have a function at the end which gets the state and produces the result. So we have this callback for end of stream. Perfect. There's some other stuff as well with collector, like characteristics, etc., but that's not super important for this purpose. So let's just have a look at collector and evaluate that against the requirements. So clearly, a collector takes n elements and produces one resulting element. So it doesn't support any of the other modes. We cannot support infinite streams because there's just no way for us to say that we've had enough. We want to not consume any more elements. Clearly, collectors can be used both in a stateful manner and a stateless manner because your state type could be void, right? So we can get both of them. So that's fine. We have that requirement under control. And of course, as we said before, we cannot end early, so we cannot express frugal operations. And since we need to provide this combiner for parallel streams, we cannot essentially state in the operation that this is an inherently sequential operation, but still do the right thing. And of course, we have the finisher, so we can actually get an end-of-stream callback. So this is the end result if we have collector measure up against the requirement. So it's clearly needs some work. All right, so this gets us to stream gatherers. So if collector doesn't fit the bill, we need something else that does. So collector is gatherer is an interface which is heavily inspired by collector, and tries to make sure that whatever is added fits. It looks like it's been there all the time. So let me describe gatherers. So first of all, it's a sequence of JEBs. And they were introduced in Java 22, so as JEB 461, and then as a preview then, and then a follow-up preview for Java 23, and for Java 24, for today, we now have stream gatherers in Java. So when you download Java 24, you can start using this as a final feature. So what does it look like? Well, as I said, it was inspired by collector, so that looks pretty similar to collector. It's still the type of the input elements. It's the state type or the accumulator type. But in this case, the R is not the single result, but it's the type of the output of the gatherer. So it's the type that goes to the next step. We have an initializer, which is the exact same thing as the supplier for collector, so it creates the state type. But now, instead of having this by consumer for each element, the accumulator, we have something called an integrator, and I will explain in detail what that does shortly. We also have the combiner, looks exactly the same as for collector, and then we have a finisher as well, also slightly different from the collector. If you recall, the collector's finisher was a function, and in this case, this is a by consumer. And the reason for that is we need to be able to produce more than one element as a result. So let's just look at the main differences here. So instead of by consumer, we have integrator. And the integrator has an integrate method. And this is a single abstract method interface. So we're going to call some integrate function with the current state, the next element, and a handle to the downstream, so that we're able to, for each element, we can decide whether we want to push elements to the next step, the next intermediate operation. But in the collector case with the by consumer, we have nowhere and no location to send anything to. We can only accumulate at that point. And then for the finisher part, we get a downstream handle to the next intermediate operation that we can use to push information to. What is a downstream, you ask? Well, it has a single abstract method called push, and that takes an element and returns a Boolean. And the return Boolean part is really important here because that return value is whether that downstream wants to receive any more elements. And by knowing whether your downstream wants any more elements, you can now propagate that information upstream. And as you may recall from the previous slides, the integrate method also returns a Boolean, which is the same thing, which is I do not want any more elements, or I do want more elements. So if the end result is you're trying to push something downstream, they don't want any more elements, that might mean you don't want any more elements, and you'll just return that. There's also an extra method, which has a default value, and it's primarily useful in a finisher. And that allows you to essentially poll to see, does the downstream want any more elements even before I produce them? So you can imagine a sort, for instance, where you're collecting all of these things and you're arranging them in the correct order, but you can't push any elements until end of stream because you would have to sort any new elements into the total sort order. But if the downstream doesn't want any elements at the end of the stream, you don't even need to try to push the entire thing downstream. So it allows you to avoid to do some unnecessary work. All right, so that's the overall gist. Let's look at an example of a simple operation that almost everybody knows instinctively what it does. So here's how we could implement the map operation on stream using just a gatherer. So in this case, we provide a lambda, which has the shape of an integrator, to the gatherer of factory method. So that's similar to collector of. And what we say is that we do not need any state type. We're stateless, hence the underscore. For each element that we receive, we're going to apply the mapper function to that element and push the result of that mapper function to the downstream, and we will return whatever the downstream push returns. So this code here is all the code necessary to implement map. And this is how we would use it. So you would, as usual, the delta here between the real map and my fake map here is the gather method invocation and passing the result of creating that gatherer into the gather operation. And as you may expect, we get the results that we're looking for. So map would be one-to-one. So for each element in, we get one element out. It's stateless, so we do not need to keep track of any information. And we're also parallelizable because we do not have any state. Let's look at something more advanced. mapMulti, which is rather recent comparatively. How would we implement that? This is the full implementation of mapMulti using gatherers. So instead of having a function, we have a by consumer, and that by consumer will get a consumer that represents the action of pushing something somewhere. So now we will say that pushing something somewhere means call push on my downstream, and when we're done here, I will return whether the downstream is rejecting or not. So the example here is we have a stream of two lists, and those two lists have each two elements. And for each of the elements in those lists, we want to call the consumer for that value. So the end result here is the list 1, 2, 3, 4. Let's do something even more advanced. Let's see how we could implement limit. So now we need to start considering state here, because limit means keeping track of some count. So for each element we encounter, we need to increment some or decrement something. So in this case, we have a method that returns a gatherer. We take the max size that we want to limit to, and then we declare a method local class called count, which we're going to use as our state. And we set the number of elements left to consume to be the max size. And now we have to decide whether this operation is a sequential operation or not. Because remember, if we're not sequential and we're stateful, it means what? Because what counts are we keeping track of, and how would we merge the counts together? What does that mean? So limit is an inherently encounter order operation. So it's a sequential operation. So in this case, what we say is that our state, our initializer, which is a supplier of some state, is calling the new, or calling new on the count class that we created. And for each element, so we declare this lambda, which is an integrator, we get the current state, which is the count, we get the next element, and we get the downstream handle. And now for each element, we need to decide, okay, should we abort at this time or should we push this element downstream or not? So first we check, do we have more elements left to count? And if that's less or greater than 0, then we don't want any more elements. We're already done. Otherwise, we just decrement our counter, we push the element downstream, and if the downstream wants more elements and we still have an element count left, then we also want to have more elements. So in essence, if we try to use it, we can limit the stream to this count. All right. Now, up until now, we've used this gather.of factory method. And it's definitely possible to implement the gather interface yourself if you want to. There's a bit of a progression. You might start doing an inline declaration in your code, your own gatherer of, and then you decide, oh, this is a super useful thing that we're doing all the time in this subsystem. I might want to pull that out as its own thing. So you can actually move it out to be its own class, its own type, with its own maintenance cycle. And in this case, we're just exploding it into a method local class definition. But you could see how you could just move this outside of the method itself. All right, so how do we then take these things that we've defined, these gatherers, and how do you actually run them? I'm going to try to explain that, and feel free to ask questions. It's a bit tricky. So I'm going to try to explain the abstract recipe here and then show you some code. So first of all, if we want to evaluate this gatherer, we have to decide where does the output go? Where are we going to send the result of evaluating the stream? So we need to first define that. And now we need to obtain the state that we're going to use. So we call the initializer method on gatherer, and then we call get on that supplier, and now we have an instance of that state. Okay, so we have the state and we have the destination. Now we need to know what to do with each element. So we call the integrator method, and we get the integrator. And now, for as long as we have more elements, and as long as true is returned from calling integrate on the integrator with the state, the next element, and our downstream handle, we just repeat. So we try to process as many for as long as the integrator wants to. Once we're done with that, we get the finisher, and then we pass in the state to the finisher and the downstream handle, and we're done. So in code, this is an ad hoc implementation of sequential gatherer evaluation on the outside. So as we said before, we need to define what the destination of the evaluation is. We have a method here that takes an iterator, which is a source of elements. We have a gatherer, and we have a consumer, which is the destination of the information. So first, we create a downstream of this consumer, and this consumer will always consume. So there is no short circuit by the consumer. We get the state, we get the integrator. For as long as we have more elements, and as long as integrate returns true for the state, the next element, and the downstream, we continue. We call finisher with the state and the downstream, and that's it. So if we call this evaluate method with a list that we obtain the iterator of, we pass in a ad hoc gatherer that just consumes strings and does 2 uppercase on them and pushes them downstream. And we will want to have system.out.println as the destination of this evaluation. This is what it does. So it prints out foo, bar, and bass, which is the uppercase version of these things. So clearly, this is just for demonstration purposes, but I think you could see how the machinery fits together and how it works. But how do we do the parallel version of this? Well, if we have a source of information and we want to parallelize it, we need to split that up. We need to take that source and we need to create multiple different chunks of it that we can process in parallel. So first of all, we recursively split the upstream data, the source data, until we have small enough chunks that we think they are useful to work on. And then per each leaf of these, we create a downstream where the output should go. And then for each of those, we also get the initializer state. So we create these small sequential evaluations out that leaf, and we just run those small parallelized sequential applications side by side, and then at the very end, we'll have to combine them all together in the tree until we get to the root of the tree. And once we get to the root of the tree, we can call the finisher once and once only for the end result, and then we're done. So this is slightly more advanced in terms of how you actually get this to work. So I figured I might actually want to visualize this somehow. So bear with me here. So these boxes here, you can view them as tasks. And the list within the box is the source elements available at that side. So if we start out parallel evaluation for this, we have a splittable 0 through 9 list of elements. And we fork that into two distinct parts. So we split that source of elements. Now we have one left and one right. And then we split again. And now we decide, OK, this is small enough. Let's process this. So imagine that we are summing things together. So each of these leaves at the bottom will be summed together. So we have a result on each, a partial result. And then we combine at every level above. So we combine the left child and the right child's result, and then that becomes the result of the intermediate branch. And then we just recursively do that until we're done. So fairly simple. And then we call the finisher with the downstream. But when you need to support short-circuiting or frugal evaluation, being able to only consume a prefix of the stream, how would you do that? Well, let's take an operation like take while. So we want to take while the element is less than 4. So we do what we did before. We split things up into small manageable chunks, and then each of these leaves will see that there is an I 4 or greater. So all of them will say, oh, I don't want any more elements. So all of them are sort of conflicting about who saw the element first, right? So how do we deal with that? Well, we can still, in this case, since there are no elements to the right-hand side, we could just recursively merge up, right? And then we're done. We get the correct result anyway. But how would you deal with that if you have a short circuit signal? Because you don't want to, if you have an infinite stream and you're recursively splitting and you are done at some point in the order of the stream, you don't want to continue to process infinity on the right-hand side, right? So what we do is that whenever we see a short circuit on a leaf, we cancel all the tasks that are going to deal with things that are after this chunk in the encounter order. So we don't necessarily need to deal with those. We can discard them. But we can also provide a little bit of a trick, because if the stream is ordered and we have a short circuit signal, we can decide that if the left-hand side of two leaves, if that short-circuited, we will not merge it. So we will just silently discard the right-hand side, and we will propagate that short circuit signal up the tree. So then we just keep the output of the earliest thing that short-circuited, which means that we're still emitting the correct results. So in this case, we could just discard those tasks, and we could merge all the way up. All right. So we have now seen how we can define our own gatherers. We can do it in more of an ad hoc style, and we can create our own implementations, and we can have our own classes, and we can all maintain that. But clearly, there are some useful gatherers that would make a lot of sense to ship as a part of the standard library. So just as there are java.util.stream collectors, there is now java.util.stream.Gatherers, which is a is the home for some of these out-of-the-box batteries included gatherers. So I'll show you some of those because I think that they are super useful to know. Folding, left folding in this case, being able to take an operation, give it a supplier of some state, and then a by function of combining the current state with the next element to return the new state, allows you to, in this case, in the first example, it's the string 1, 2, 3, 4. It's not the number 1, 2, 3, 4. But the same operation with ints and 0 as the empty string in this case, you would get a summation of these values. So folding is super useful, and it allows you to define a different result type or output type compared to reduce, where reduce is more restricted. Scanning is almost the same thing as left folding, but what it does is that it emits every intermediate result. So let's say you have a transaction log on your bank account, and you want to see the current balance after each transaction, but you still want to decrement or add depending on what kind of transaction it is. Scan gives you the intermediate results applying this function. So in this case, you can see that you get the string 1, string 1, 2, string 1, 3, 1, 2, 3, and string 1, 2, 3, 4, etc. Windowing functions. There are many of them. We've decided to ship with 2. So window fixed is fixed window functions. And you supply it with the size of the window that you want to have. And that gives you immutable lists of that size up until the very end. And of course, if you don't have enough elements to fill the entire window at the end, we're going to cut that short, but we don't discard any elements. So it's up to you to decide if you want to keep the last or not. We also have an interesting one here called mapConcurrent. And imagine that you want to do something very targeted in parallel or concurrently. Let's say that you want to call some cache, or you want to call some service or something, and you just want that specific thing to be concurrent, then mapConcurrent is the thing. So what it does is that it evaluates a function using virtual threads up to a certain limit that you give. So in this case, we have the numbers 1, 2, 10, 20, 30, 40. And for each of those values, we're going to sleep for that amount in seconds. And we have set our max limit to 5 here. So we only do 5 at the same time. And whenever we get interrupted, we reset the interrupt and we return the value. And if we put limit 2 on this stream, so we have 6 elements, and we will sleep for at most 40 seconds, but we only want the 2 first, in which case we will only have slept for 2 seconds. We would expect this to exit early after 2 seconds rather than 40. And that is what it does. So if we have a short-circuiting operation afterwards, then that gets propagated to the mapConcurrent, which will then interrupt the previous operations. So that's super useful. I have another interesting point here, and I think this is a very, very subtle thing. So a gatherer has an and-then method, just as function has an and-then method. So you can compose gatherers in a similar fashion that you can compose functions. So let me show you what I mean. So let's say that we have some gatherer that takes strings and produces an optional integer, so it's a parsing gatherer. And then we have another gatherer which takes optional integers and just emits those who are present, right? So we discard the empty optionals. So if we gather the parse ints and then drop the empty ints, we would expect to get only the things that cleanly parse to integers. So 2 consecutive gathers here is equivalent to combining the first gatherer with the second gatherer. So now you can take one gatherer and make it more sophisticated by combining it with another, but it still looks very simple. So First, you have string to optional integer, and then you have optional integer to integer. And the resulting gatherer of combining those two is a gatherer from string to integer. So now you can build something more complex out of simpler parts. And it's interesting to note as well that subsequent gather operations are virtually like composition of those gatherers. So if you sort of squint, as we said before with the stream pipeline, if you have a split iterator, some source of elements, and you have 0 to n number of gatherers, and you add a collector, that is essentially the recipe for stream pipelines. Because virtually any intermediate operation can be represented by a gatherer, and virtually any terminal operation can be represented by a collector. So, to sum things up, what features do gatherers support? Now, clearly, this would have been weird if I managed to omit something here. So, Gather supports all of the interesting features that we wanted to support in a packaging that looks very similar to what we already had there, like collector. There's a single new method added on stream. It has a default implementation as well, so it doesn't break any existing code that implements stream. And it gives us the building blocks for intermediate stream operations. So it allows you to do stateful or stateless operations, any ratio between inputs and outputs, allows you to consume only a prefix of the stream. It allows you to say that this operation is only ever to be executed sequentially, or this operation is parallelizable. You can compose them together, and it is now final in Java 24. I'll take questions. Thank you.
Is the API surface for the map concurrent and the structured concurrency JEP that's coming at some point, are those likely to kind of meet at some point in the middle?
Yeah, so that's a great question. So it's about the relationship between map concurrent and structured concurrency. The thing with structured concurrency is that it's still a work in progress. And map concurrent is something that could be at some point related to structured concurrency, but it is currently not. There are several reasons for them. It's slightly technical, but we're still looking to find the ideal representations that make certain aspects easier to deal with from a concurrency point of view. So there's some interesting new work in structured concurrency for hopefully going in soon. So stay tuned. We've received a lot of good feedback on structured concurrency, so that's always great. Always happy to get more feedback on structured concurrency. But yeah, great question. Anyone else?
Hi there. I was wondering, have you re-implemented the existing pipeline stages in terms of gatherers? And if not, how do the performance characteristics compare?
Great question. So during the exploratory phase of trying to come up with what would something that is the archetype for intermediate operations, one of my goals was I need to be able to re-implement the streams interface using only this abstraction. Otherwise, I have clearly failed, right? It's a hard thing to ask or answer because certain operations are easy to express as a general thing, but they are not optimal as the general representation. So clearly, if you have more knowledge about the internals, you know exactly which corners you can cut, and you can be more expressive about which information that you can provide. So while it's easy is probably not the right word. While it's possible to re-implement streams on top of gatherers themselves, sometimes you actually have more information in your stream implementation just because you don't simply know that it's a gatherer, but you know exactly this is how my implementation works. This is the exact needs of the operation itself. I can do that in a more clever way if I don't express it as a gatherer. So I would encourage or inspire you to see if you can implement Stream on top of Gatherer just to get a sense of what it's like.
Thank you.
Thank you.
How do you determine which things should go into the Gatherers module? Like,
Yes.
yeah.
That's a great question. And it's also, are we just moving the goalposts? First, it was, oh, it's difficult to know if we're going to include something on Stream, but now you just moved it, and what gets included in Gatherers. I think we are seeing already, and during the preview of Gatherers, we are seeing people picking this up, and we're seeing what people are able to do. I think the good thing here is that before, it was really tricky to experiment with your own intermediate operations. You would essentially have to implement streams yourself. So right now, there's much more opportunity for people to experiment, try things out, improve, and then over time, propose and say, hey, we've now used this for a while. We've ironed out all the issues that were there, and we think this is a super useful thing, and then we can have that conversation. But there's no checklist or anything like that, and of course, we don't want gatherers to end up having 1,000 methods either. But it's more specified, and it doesn't get. Whenever you type dot on a stream, which is fairly common that people do, you wouldn't want to have 100 or 200 methods on there. Yes, thank you.
How would you zip two streams together?
How would you zip two streams together? Great question. That entirely depends on how you implement streams. So there is a choice that you have to make, whether you have a pull-based stream or whether you have a push-based stream. And depending on whether you choose push or pull, you're going to have merging or forking being your main issue. So implementing zip, for instance, means you need to be able to ask for information from two different sides. And if you're a push-based stream, those two sides are going to try to push to you. So clearly, they can't push at the same time. They would have to push from different threads. Right? So in the general case, zipping requires a pull-style operation, and fan-out requires a push-style thing in general, because you would have to negotiate otherwise who should get the element first. So great question. There is no, for the reference implementation in the Java standard library, there is no straight, because those are push-style streams, so there is no easy way to get to a general zipping functionality. But what you can do, if you're willing to accept that one of the legs of the zip is not a stream itself, it's fairly trivial. So if you accept that on one hand you have an iterator, or on one hand you have a list or something like that, then it's fairly straightforward. But yeah, it's a great question. I have lots of things to say about this problem. Thank you. Cool. I'll be around, so don't be a stranger, and have a great conference. Thank you.